this coil is expanding. What is the meaning of expanding? Expanding means the area of the coil is increasing. Area of the coil is increasing, and we
Yes.
have to find the direction of the induced EMF. So we know that the magnetic flux linked with the coil is given by VA cos theta.
Yes.
Okay. So magnetic field is constant here, and this cos theta will also constant. Why the cos theta is constant? Because the angle between theta is the angle between the area vector and the magnetic field.
Yes, sir.
So theta will be 0. Theta will be 0 degree because magnetic field is in z direction
Yes.
and the area vector also is in z direction because area vector is perpendicular to the plane of the coil. Okay. So if we are considering the screen as a xy plane, then magnetic field is in z axis and the area vector also in z axis, means both are in same direction, that is area vector and the magnetic field. So angle is 0. Now this V is constant. This cos 0 is 1. So you can say your magnetic flux will be directly proportional to the area. So your area is increasing or decreasing. So your area is increasing.
Yes.
It means that your magnetic flux will also increase because magnetic flux is directly proportional to the area.
Yes.
So we know that whenever the magnetic flux is increasing or decreasing, there is induced EMF in the coil.
Yes,
So
sir.
there will be induced EMF in the coil. So there will be the induced current in the coil. And here the magnetic flux is increasing. Your flux is increasing. So induced current will try to decrease this current, decrease this magnetic flux according to the Lenz's law.
Yes,
So
sir.
induced current will decrease. This is a sign of decrease in decrease in the magnetic flux. Okay, decrease in magnetic flux. Okay, so how the induced current can decrease the magnetic flux? By decreasing the magnetic field.
Yes,
So
sir.
how the magnetic field can decrease? The induced current will induce a magnetic field in the opposite direction of the given magnetic field. So induced magnetic field will be there in the outward direction. Okay,
Okay, sir.
this is your induced magnetic field. In the outward, why in the outward direction? Because overall the magnetic field will decrease.
Yes, sir.
Okay. Given magnetic field is in inward direction, the induced current will induce the magnetic field in outward direction. So when you will take the vector sum, means overall both the magnetic field will be in the opposite direction. So overall magnetic field will decrease. Okay. So now we know the direction of the induced magnetic field. So induced magnetic field is in outward direction. So what we will do, we will point our thumb in outward direction and curl fingers.
Yes.
Right, we will use right hand thumb rule. Point your finger, towards the direction of the magnetic field, and
Yes.
sense of curl of your finger will give you the
Yes.
direction of the induced current. So this is the
Yes.
induced magnetic field towards me, means outward direction. You will curl like this. So this will give you the direction of the induced current in the anti-clockwise direction.
Yes, sir.
So induced current will be in anti-clockwise direction. So direction of phi will be anti-clockwise, and this is given by right hand thumb rule. Okay, note it down. Okay, now take the screenshot.
Done, sir.
Okay, so now we will discuss the motional EMF. MOTIONAL, motional. So
Yeah,
here
sir.
from the name you can guess motional, means
Yes, sir.
here is term motion.
Yes.
Okay, so first case we will take when a wire will do the linear motion in the magnetic field. Okay,
Yes.
we will have, this is a wire
So
Okay.
can you zoom out, sir?
Zoom out, yes.
Yeah.
Okay. So basically this is your wire, and this wire have the length L, and this wire is moving in a magnetic field. So the induced magnetic field, or not induced EMF, will be minus V into L into V. This is also known as motional EMF. Why? Because this EMF is induced due to the motion.
Yes.
Okay, so motional EMF due to the motion of the conductor in magnetic field, and this is the whole condition. Now, motional EMF is given by magnetic field into length of the wire into the velocity with which the wire is, or the conductor is moving in the magnetic field. Okay, so this is wire AB. AB is your wire, or wire means you can say conductor. Now we will derive this result. We will derive this result. This is very simple. So now I am taking a frame. I am taking a frame, and this is our wire AB. Just a minute. This is our wire AB. Okay, so this wire can slide on this frame. Okay, this wire can slide on the frame.
Yes.
Okay, just let me explain what is happening here. Okay, see, suppose this is your frame.
Yes.
This thing is your frame, and this just a minute. This is your frame. Okay,
Okay.
and on this frame there is one wire, and this wire is allowed to move on this frame like
Yes.
this and like this, like this and like this. Are you able to get it?
Yes. Sir.
See, actually what is happening, we have a wire and we have a frame. So initially suppose the wire is here, now wire is moving with constant velocity v. So this is the case here we have. So here what will happen, when the wire will move with some velocity, okay, when
Yes.
the wire will move with some velocity, then this area, this will become a coil. This is a coil, you can say this is a coil AB, and you can take this point as C
Yes.
and D. So this is our wire AB, okay,
Yes, sir.
and this becomes the coil A, B, and C and D. This is the semicircle here. This is also a semicircle. This is representing that the wire is able to move on this frame. This is your frame.
Yes, sir.
This is your frame. Okay. Suppose right now the wire is moving with some velocity, and the position of the wire is here, and this distance is x. So when this wire will move in this direction, this x will increase or decrease? When the wire will move in this direction, increase, na?
Yes,
Very
sir.
good, very good. X will increase. Now you can see this ABCD is a rectangular coil.
Yes, sir.
ABCD is a rectangular coil.
Yes, sir.
Rectangular coil. So we know that area of a rectangle, and we know that the length of the wire is L. So means this length is L, this length is X. So what is the area of the frame or area of the coil? L into X.
Yes, sir.
Yeah. Now how EMF will be induced in this wire? Because what is happening here, see, when this wire will move in this direction,
Yes, sir.
so area will increase,
Yes.
area of the coil will increase, and we know that the flux is given by VA cos theta. Okay, theta will be 0 degree here, magnetic field is constant, so your magnetic flux is directly proportional to area.
Yes, sir.
So here your area is increasing or decreasing? Increasing, na?
Increasing.
Okay, very good, very good. our area is increasing means our flux will also increase. So this area is
Yes, sir.
increasing, so magnetic flux will also increase. What
Yeah, sir.
happens when the magnetic flux increases? According to the Faraday's law of electromagnetic induction, we can say whenever there is a change in the magnetic flux linked with the coil, there will be induced EMF in the coil, and
Yes,
that
sir.
induced EMF is given by minus d phi by dt,
Yes, sir.
according to the Faraday law. This is from Faraday law. Okay, so this is your phi. Now put the value of phi here. So we will get E is equal to minus dy dt of phi. What is phi? BA cos theta. What is area? Instead of area, you will put L into X.
L into X. Yes.
Yeah, and you will here you will put cos 0. Why? Because you can see what
It's
is the
constant.
theta? Yeah, theta is the angle between the area vector.
And magnetic.
So area
Yes.
vector and magnetic field are in same direction, means Z direction.
Yes, sir. Yes, sir.
Okay,
Okay, sir.
so now cos 0 is 1, and you can take this magnetic field out of the differentiation. Length is also constant, so V and L will be constant. So here you have dx by dt. Can you tell me what will be the dx by dt? Hmm? This x is changing. X is what is x? X is a distance.
Yes, sir.
Distance divided by time. What is distance divided by time? Speed, na?
Yes, sir.
Speed, or you can say displacement divided by time
Yes,
is
sir.
velocity. So you can
Yes.
say dx by dt is equal to the velocity of the wire. So your EMF
Sir.
induced in the wire is given by minus B into L into V. Got it or not?
Yes, sir.
So this remember, this will be the induced EMF in this wire AB. Okay, so you can write here. I have already written here. This is the induced EMF in wire in conductor. Again, this is the same result. E represent the induced EMF, small e.
Yes, sir.
Now this is our coil ABCD. So we will see what will be the induced current in this coil. What will be the induced current? So this is your wire AB. This is your CD. Okay.
Okay, sir.
Okay. So, जी हाँ So, okay, Ziyad. So see, this is our coil ABCD. So
Yes, sir.
there will be the resistance of the coil. Okay, there will be the
Okay, sir.
resistance of the coil, and we know that current is EMF divided by the resistance. So current is EMF divided by the resistance. So current I is equal to what is the value of EMF minus VLV divided by R. So this will be your induced current. This will be your induced current in the coil. Now we will find the induced charge. Okay. Charge induced we can calculate with current. Induced charge. We know that current is given by dq by dt.
Yes.
Current is given by dq by dt. Okay. Okay. So first write down this, then we will discuss.
Okay.
Just a minute. I am just changing it.
Okay.
Okay. So you can take the screenshot.
Done, sir.
Done?
Yes.
Note down this.
Done, sir.
Okay. This is your proof. Just 1 minute. You can note it here.
Okay, sir.
Now take the screenshot. This is plus x. Okay. This is plus x is representing the wire is moving along positive x axis.
Positive. Okay, sir.
Yeah. Note down this.
Done, sir.
Okay.
Done, sir. Done, sir.
Okay. Now, we will discuss actually this thing.
So you were writing induced charge, right?
Induced charge, actually there is no requirement of that because we will calculate the magnetic force. Okay.
Okay. Okay.
We'll calculate the magnetic force. So now you should analyze this. What is happening? This is the wire AB.
Yes.
We have this wire AB. Okay, and this wire is moving linearly. This wire is not rotating. Remember,
Yes,
this wire is
okay.
moving, doing the linear motion.
Yes.
So due to that linear motion, what is happening? Finally, what is happening? The current is there in this wire. There will be induced
Yes,
current.
sir. Yes, sir.
Okay. Now, I have told you this thing. I have told you whenever this is wire, this white color thing is a wire, and
Okay.
this wire have the induced current. This wire have the induced current. This wire have the induced current, and this wire have the length, and there is the magnetic field also.
Yes.
So whenever there is a current carrying wire in the magnetic field, there will be the magnetic force on that wire.
Yes, sir.
Okay.
Okay,
There will be the magnetic force. Okay. Now, and the formula of the magnetic force on the wire is given by ILV sine theta. In vector form, it is written like this. In
Yes.
scalar form, we can write. Basically, we will use this formula.
Okay, sir.
Okay. So, have you understood why we are calculating the magnetic force on the wire? Because there is a current in the wire, induced current, and due to that induced current in the wire, and that wire is present in the magnetic field. And due to magnetic field, there will be the induced, there will be the magnetic force on the wire.
Yes, sir.
Okay. So basically, we will focus on this wire AB. This is our wire AB. This wire is moving with some velocity, and now we will calculate what will be the force on this wire. This is very simple derivation. So what you will do here? Okay. Force is given by force on wire AB, current in wire AB into length of wire AB into the magnetic field in which the wire is present, and sine theta. Achha, what is theta here? Theta is the angle between the length vector and the magnetic field. Or you can say here the current is along the length, so you can say the angle between the length of the wire and the magnetic field. What is theta? Angle between current vector, you can say length vector. It's better to write the length vector. MF means magnetic field.
Okay.
So here, see here, this is your magnetic, this is your direction of the current, induced current.
Yes.
When you will apply the length law and the right hand thumb rule, you will get the anti-clockwise direction of the induced current. So this induced current is along y-axis and your magnetic field is along z-axis. So what will be the theta? 90 degree.
Yes, sir.
See, this current is along y-axis, and this magnetic field is along z-axis.
Yeah, okay, sir. Okay,
so,
sir.
Okay. Now, force on wire AB. We will put the value of current. Current is given by minus of VLV divided by R. So we will put here minus of VLV divided by R into length of wire. I have put the value of current. Now length of the wire into the magnetic field and sine 90. Sine 90 is 1.
Yes, sir.
Force on wire AB is given by minus V square L square VYR. This will be the force on the wire AB. Okay, this is the force on the wire AB. If you will just write the magnitude of this force AB, okay, only the magnitude. So this will become V square L square V divided by R. This is the only the numerical value. Numerical value, or you can say the magnitude. Okay, now see, I have told you about this. The direction of this force, okay, the direction of this force is given by point your fingers along the direction of the current.
Yes.
And curl toward the magnetic field. Okay, so we will calculate the direction of the force here. Okay, so here this magnetic field is inward direction. Magnetic field is in inward direction and current is along the positive y-axis.
Yes.
Okay, so now see, point your fingers along the current.
Okay.
And magnetic field is inward, like
Inward.
this,
Yes, sir.
away from me. So
Yes.
direction of the force will be
Yeah.
negative
Yes.
z-axis.
Negative. Yes. Z-axis. Yeah.
This will be FAB. So force on the wire AB carrying a induced current I in the magnetic field B, B is the magnetic field, is along negative Z direction.
Yes.
Negative X direction.
X. Yes, X.
Negative X direction. Okay. And this wire is moving with the constant velocity. According to the Newton's first law, according to Newton's first law, you can say that if a body is at rest,
Yes.
or if a body is moving with the constant velocity, the body will continue to move with the constant velocity or will remain at rest until and unless there will be an external force on it. Okay.
Okay.
So means, or according to the second law, this wire is moving with constant velocity. So wire is moving with constant velocity means there will be no acceleration. There will be no acceleration of the wire. So you can say there will be no net
Yes.
force on the wire.
Yes.
So net force on the wire should be zero so that the wire will move with the constant velocity. The wire can, anybody can move with a constant velocity only when the net force on that body is equal to zero. According to Newton's second law.
Yes.
Okay, so now here it means that this is your positive x-axis. So it means that an equal and opposite external force you have to apply. Equal and opposite external force you have to apply to move this wire with constant velocity. Okay.
Okay.
So here you will write an equal and opposite force F external is applied on wire AB to move this wire with constant velocity V. With constant velocity V. So you can say that your external force is negative of that force on wire AB. Can we say na? Both are
Yes.
equal but in opposite direction.
Opposite. Yes.
Magnitude wise, they will both the forces will be same magnitude wise. If you will talk about the magnitude of both the forces, then you can say both will be equal. Now, I have already written here this statement of right hand rule to calculate the direction of the force due to the induced current. Okay, I have told you na.
Yes, sir.
Point your fingers towards the
Direction.
current
Yes.
and
Yes.
curl towards the magnetic field, whatever the direction of the magnetic field.
Yes.
Thumb will give you the direction of the magnetic force.
Magnetic force.
Okay. So now we will discuss the mechanical power spent. What is the meaning of mechanical power spent? Why mechanical power is spending? Because an external force is applied
Yes,
here to maintain the constant velocity of the wire. Okay, so
yes.
mechanical power is spent is given by, I will represent this with capital P, and mechanical power is spent. Power, what is power? Power is the dot product of force applied, external force applied, and the velocity. So here, this force, you are applying, and this wire is moving with a velocity of v. And what is the angle between the external force and the velocity, Ziyad?
Between the
Uh, Angle between this external force and this velocity.
zero, then.
Yeah, very good. 0 degree.
Yeah.
If both are this arrow, arrow represents the direction.
Yes, sir.
Okay, so 0. So dot product of two vectors, we can write magnitude of A, magnitude of B, and cos of theta. Okay, so
Yes, sir.
when you will open this dot product, you will get F external into velocity into cos theta. Acha, theta is equal to 0 degree.
Yes, sir.
So you will put here cos 0 is equal to 1. So your
Yes.
answer will be F external into
Okay.
velocity. Okay. Now what is
Yes.
the value of F external magnitude wise? F AB?
Yes, sir.
I have written here na. F external is equal to FAB, force on wire AB. And what is the force on wire AB? V square L square V divided by R into V.
Yes, sir.
Okay. Now your mechanical power spent will become VL V square L square V square by R. So you can write the mechanical power spent VLV by R and the square of this. So this is your mechanical power spent. This is your force. Okay, this is your force. Force on wire. Force on wire, and this is your mechanical power spent.
Okay.
And what is your motional EMF? This is your induced current, and this is your motional EMF. Where is this? This is the motional EMF.
Yes, sir.
So you have noted this. All this you have completed this now. Induced current.
Yes.
Okay, so now take the screenshot.
So can you zoom out a little bit?
Zoom out. Okay.
Yes.
More?
Yes. No, enough.
Actually, I am not zooming out now because that the writing becomes thin.
Okay.
When we zoom, the quality of the writing decreases.
Okay.
Yeah. Okay, no problem.
I can still read it.
Now it's
Yes.
done.
Yes. Done.
So this is your note point.
Okay.
Write down this also note point.
Done.
Now I am zooming out.
Okay. That's
Okay, so what is the motional EMF? E is equal
is
to,
equal to minus BLV.
very good. E is equal to minus
BL
V into LV. What is the mechanical power spent? VLV square
square
by
by
R.
R. Yes.
So these two formulas you should know.
Okay.
So here is one wire AB. Okay, and
Okay.
this wire is moving in the magnetic field with 5 meter per second, and the strength of the magnetic field is 2 Tesla, and the resistance of the wire is given as 5 ohm. We
Yes.
have to, and the length of the wire is 10 meter. We have to calculate the induced EMF and the electrical power. Acha, one thing more I want to add here. Hmm, this this is the mechanical power, na? This is the mechanical power, and this mechanical power is equal to the electrical power, because electrical power means the due to the induced current in the wire, due to the
Yes.
induced current in the wire, there will be the magnetic force in this direction. See here, due to this force, na, due to this
Yes.
force, the wire, the force on the wire is in this direction, but you are applying the force in this direction. Okay,
Yes.
means
Yes.
your mechanical power expended, your mechanical power expended is converting into the electrical power, because what is
Yes. Sir.
happening when you are pulling the wire, when you are pulling the wire like this,
Yes.
when you are just applying a force on the wire in this direction, what is happening, there will be the induced current in the wire,
Yes.
means
Sir.
by the mechanical energy electrical
Yes. Sir.
energy is produced.
Yes.
Current means the electrical energy, so you can
Mm.
say the mechanical power is equal to the electrical power. So here you can write mechanical power is equal to the electrical power, that is equal to VLV square by R. Actually, see here what is happening. Initially, we have a frame. Okay, initially we have a frame in the magnetic field.
Yes. Sir.
Imagine this is a frame, and on this frame, this wire is moving. So initially we have a frame in the magnetic field, and this is our wire. So as this wire is moving in this direction, so this this become now a coil, this part become a rectangular
Yes. Sir.
coil. So when this
Yes. Sir.
wire is moving in this direction, so area of the coil is increasing. So how the area is increasing, because you are applying a force on this wire,
Mechanical. Yes. Sir.
you are applying a mechanical force,
Yes. Sir.
or you can say you are just giving the mechanical power to the wire.
Yes. Sir.
So after you have applied the force on this wire, after that the current is inducing, na? Means
Yes. Sir.
your mechanical power is converting into the electrical power. Current means
Yes.
the
Sir.
electrical power.
Yes. Sir.
Okay, so that is why in the question, if electrical power is asked, then you will calculate the mechanical power, because both will be equal.
Okay. Sir. Yeah.
Okay, so here uh, induced EMF. Induced EMF is given by minus VLB,
Yeah.
minus 2, length 10, velocity 5. This will become 100 volts. Mechanical power, electrical power is given
Mm.
by VLV square
Yes. Sir. By R.
by R. So what is the VLV square? You can put the values. Magnetic field is 2. 10 5 square. Why? Resistance of the wire is 5. So you will get 2000
Yes, sir.
watt. Okay, note down this.
Okay, sir. Done, sir.
So there is one note point here now. When this is your wire, suppose, and this wire is moving in the magnetic field with this velocity v. Okay,
Yes.
with this
Okay.
velocity v, and this velocity v is making an angle theta with the wire. Then in that case, you will take the component of the velocity. This is the perpendicular component. This is the parallel component of the wire.
Yes.
Okay, so this component is the perpendicular component. Why this is perpendicular component? Because this direction direction of this v sin theta is perpendicular to the wire,
Yes, sir.
and this v cos theta is along the wire. So you are saying that this is a parallel component.
Yes.
So your induced EMF in the wire. This is your induced EMF.
Yes.
Or you can say induced EMF across ends of wire is given by minus VL, okay, length of the wire L, and here you will take the perpendicular component of the velocity. Okay, here you will take the perpendicular component of the velocity.
Okay,
So
sir.
this is one point, and another point is this. This magnetic field, length, and the velocity, these are mutually perpendicular. Mutually perpendicular means like x-axis, y-axis, and z-axis.
Okay.
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 So magnetic field is perpendicular to length. Length is perpendicular to velocity. Velocity is perpendicular to magnetic field. So this is the another point. So now you can take the screenshot of this.
Okay, sir.
This is your first note point.
Done, sir.
Okay. Now note down this point also.
Done, sir.
Okay. Once you have asked me a doubt, means when a wire
Yes,
is
sir.
rotating in the magnetic field,
Yes.
so what will be the induced EMF? So that was this topic. I have told you na there. This is the,
Yes, sir. Yeah, okay, sir. Yeah.
so induced EMF across the ends of the conductor means when your conductor is rotating.
Yes.
Okay, this AB is your conductor, and this conductor is rotating. This conductor is rotating about some axis.
Yes, sir.
This conductor. So suppose this is your conductor AB,
Yes.
and this conductor is present in the magnetic field. So this conductor is rotating like this.
Yes.
Okay. So due to the rotation of the conductor, there will be the induced EMF in this conductor. So we will see how the induced EMF will be there. How the induced EMF will be there, and we will derive what is the value of that induced EMF. Okay. We will derive
Okay.
the value of that induced EMF. Before that, I have told you, I think, what is the angle relation between the linear velocity and what is the relation between the angular velocity. Okay, so induced EMF across ends of conductor when the conductor is rotating in a plane perpendicular to the magnetic field with angular velocity omega. So this is your conductor AB,
Yes.
and this conductor is rotating with omega angular velocity. So what is omega here? Angular velocity.
Yes.
Omega is the angular velocity. And this conductor is rotating like this with angular velocity omega.
Yes,
So
sir.
angular velocity of all the points on the wire will be same. Angular velocity, that day I think I have told you, at all the points,
Yes.
of the conductor, the angular velocity will be same.
Yes.
So once again, I am explaining what is the angular velocity. This is a circle, and this is the center of the circle. Suppose a person is moving on this circular path. So suppose initially the person is here at point A. Now this person is moving in this direction, and finally this person is here at point B. Suppose this is the angle theta covered by the person in going from A and B, A to B. So this theta is known as the angular displacement.
Yes, sir.
We have the displacement, na? We have displacement, linear displacement. So like this is the angular displacement. Okay. There will be some time also in going from A point to the B point, time
Yes.
taken by the person. So T is the time. So your angular velocity is given by angular displacement divided by the time, and your linear velocity is given by the linear displacement. Suppose x is your linear displacement divided by the time.
Yes. Okay.
This thing you should know. So when what is happening here actually, your conductor is rotating anti clockwise direction in the magnetic field. So there will be some
Yes.
angular velocity of this wire. There will be the angular velocity of this wire,
Yes, sir.
and there will be one axis of rotation about which the wire is rotating. So this is the axis of rotation. This is the axis of rotation about which the wire is rotating, like this.
Yes, sir. Yes.
Okay, so this axis of rotation is very important. Remember, so the wire is rotating about some axis of rotation. So the angular velocity of this all the points on the wire is same, because all the points will swept equal angle in equal interval of time. That is why the angular velocity of all the points on the wire will be same. Okay.
Yes.
And if you want to calculate the linear velocity, linear velocity of all the points on the wire will be different. Linear velocity of, suppose this is the case of the a man moving on a circular path. So if I want to find the direction of the linear velocity, okay, direction of linear velocity will be tangential. This is suppose v1. In this direction, this will be the direction of the velocity, tangential. And remember that the linear velocity is equal to the radius into angular velocity if the body is moving in a circular path. What is this? Linear velocity.
Yes, sir.
And what is omega? I have already no. Omega is the angular velocity.
Angular, yeah.
Omega is the angular velocity. Okay.
Okay.
So this relation you should know. What is the relation between omega and theta? And what is theta? And one relation is this you should know. V is equal to R omega. Now this wire is rotating in a circular path in this direction. This is wire AB, and this wire AB is rotating in a circular path.
Yes, sir.
This condition is given with angular velocity omega. So as this wire is moving in the circular path,
Yes.
not a circular path, means this whole wire is rotating.
Yes,
This
sir.
whole conductor is rotating towards the axis. So if you will take any point on this wire, so that point will perform this circular motion. If you are able to imagine.
Yes, sir.
Okay, just a minute. Actually, first see, this is your conductor AB. So you can say the conductor AB is perpendicular to the magnetic field. The conductor AB is perpendicular to the magnetic field.
Yes, sir.
Because your conductor is lying in y-axis and your
Yes, sir.
magnetic field is along z-axis.
Yes, sir.
So what I am doing here, and when this conductor will rotate in the magnetic field, so the magnetic flux linked with the conductor will change.
Yes,
Magnetic flux linked with the conductor will change, and whenever the magnetic flux linked with the conductor or coil change, EMF induced in the conductor. So due to the rotational motion, due to the rotation of the conductor, the EMF will be induced.
Yes, sir.
And that EMF we want to calculate. So I am just taking very small element of this conductor of length dx. Okay. First we will calculate the EMF induced in that small element dx. Okay, first we will calculate that.
Okay, sir.
So this element will have a linear velocity in tangential direction.
Yes, sir.
Okay, V is the linear velocity.
Yes.
Linear velocity of element dx. What is the meaning of element dx? I have taken a very small length of this wire,
Yes,
and
sir.
I am trying to calculate the EMF induced in that small element of the wire.
Yes, sir.
And I have told you each element of this wire have same angular velocity.
Yeah, sir.
Okay,
Yes.
so each element of the wire have same angular velocity. Suppose this is the point B about which there is one axis passing from this point B and about which the wire is rotating. Okay,
Okay, sir.
This is about this, na? Here I have told you in the starting. There is one axis like this,
Yes, sir.
and this axis, and about this axis, this wire is rotating. So
Yes,
this
sir.
point of the wire is A, this point of the wire is B.
Yes.
So from the point B, the axis is passing, and about which the wire is rotating. Suppose this distance is x initially. X is a distance between this point B and this element dx. So we can write the angular velocity, the linear velocity is equal to x time of angular velocity. Okay,
Okay, sir.
x time of angular velocity.
Yes, sir.
Okay. So now EMF induced in this element dx. EMF induced, you can write here. This is the, I have already written here. Induced EMF in length dx, that will be small induced EMF and given by minus V into length VLV na,
Yes, sir.
and the velocity. So V is equal to x omega. So dE is equal to minus V into dx. Put P is equal to x into omega. Okay. So this is your
Okay,
dE.
sir.
So here is minus V into omega because magnetic field is constant and omega is constant. So here is your x into dx. So what is this dE? This is dE is the induced EMF in small length dx.
Yes,
For
small. Yeah.
for calculating the total EMF induced across the ends of the wire, you will integrate this equation number 1.
Okay, sir.
So for induced EMF across ends of conductor, we will integrate the equation dE. This will become minus V omega x into dx from, now this x is variable here. So x is at this point B, the value of x will be 0, and at this point A, the value of x will be L. Okay, so
Okay, sir.
limit of the integration will be from 0 to L. Now this will be total EMF induced across the ends. So you will take minus V omega out of the integration, and this will be 0 to L x into dx. So integration of x dx will be x square divided by 2, and you will apply the limit here,
Yes.
and this will become minus V omega into 1
Yes.
by 2 into L square minus 0 square. So
Yes.
EMF induced in the wire will be minus V omega L square divided by 2.
Yes, sir.
This is your induced EMF in the rotating wire.
Yes. Okay.
So integration na,
Yes, sir.
integration. So integration of x dx will be, this is x to the power 1 na, so increase 1 power here. This is x square,
Yes,
this
sir.
is 2.
Yes, sir.
There will be some constant. So
Yes.
I will not talk about the constant because I am taking the definite integration. So
Yeah,
here
yes.
the limit of x is equal to 0 to x is equal to 2. Okay.
Yes.
So you will
Okay.
put the limit
Yes.
x is equal to 0 to x is equal to 2.
Yes.
So this is just for example. So here this half you will take out. So now you will put the limit, put x is equal to 2 here. So this will
2.
become
Yeah.
2 square,
2
this will
square.
become 0 square.
Yes.
So accordingly you can solve.
Yes.
Suppose this is given x square into dx, limit of x is equal to 1 to x is equal to 2.
Yes.
So here is x square na, so here you will
X square by 2.
increase x cube.
X cube by 2. Yes.
X cube divided by
By
3.
3. Yes. X
Yeah.
cube by 3.
And you will apply the limit
Yes.
1 to 2.
2.
Now this will 1 by 3.
1
Now
by
you
3.
will put here 2 cube
Yes.
minus of 1 cube. Upper limit minus lower limit.
Lower limit. Yes.
So now accordingly you can solve this. So
Yes.
that's how I have solved this equation.
Okay.
If you want to see that this is given as x dx na, limit of x is given from 0 to L.
0 to
So
L.
this will become x square by 2.
Yes.
So 0 to L.
Yes.
So this will become half.
Half.
Now put the limit, upper limit L square
L
minus
square
0
by.
square.
Yes.
So this will become L square by 2.
Yes.
So that is I have this is minus b omega and I have
Yes.
written L square by 2. So one question on it we have. Okay, so write one question. A wire of length 2 meter is rotating with an angular velocity of 5 radian per second. Five radian per second in uniform magnetic field of 10 Tesla. Calculate EMF induced across ends of wire Simple question. So read the question. A wire of length 2 meter means length of the wire is given. Is rotating with an angular velocity means omega is given 5 radian
Yes. Yes.
per second. In a uniform magnetic field value is given 10 Tesla.
Yes.
So what we have to find? We have to find the induced EMF. What is the formula? Minus V omega L square by 2.
Yes, sir.
So put the value minus 10, omega is 5, length is 2 square divided by 2. What will be the answer? Minus 100 volts.
Yes, sir.
Simple question na, on the same formula we
Yes.
have just derived. So now you can note down this. Just a minute. Note down this. Okay, just wait a minute.
Okay.
Write down the heading. Angular velocity. Okay.
Okay.
Done.
Yeah. Done.
Done.
Yes, sir. Done.
Okay.
Done.
Done.
Yes.
Okay. So we have done one question also. You
Yes.
can take the screenshot of this also.
Done.
Just wait a minute. I'm just.
Notice.
Okay, Ziyad. So have you understood the derivation?
Yeah, I think so, sir. Yeah.
Means actually now what is happening earlier, we have discussed that the conductor is moving linearly in the magnetic field.
Yes, sir.
In this derivation, we have discussed what will be the induced EMF when the conductor is rotating. So the rotational concept is little bit, I will say, more complex to understand with respect to, or you can compare with the linear uh, things. Okay, actually the rotational motion, to analyze the rotational motion is little bit difficult. Okay.
Yes, sir. Oops.
Actually, why? Because in rotational motion, we should know the linear motion also. In defining the terms of rotational motion, we should know the terms of linear motion also. Actually, earlier your wire is moving with the linear velocity, and in this case that we have just discussed, your wire is rotating with an angular velocity.
Yes.
So when your wire is rotating with an angular velocity omega, okay, then
Okay.
there will be the induced EMF in that wire. Why? Why the induced EMF? Always induced EMF will be due to the change in the magnetic flux.
Yes, sir.
Okay.
Okay, sir.
Change in the magnetic flux. Okay, so we will discuss the mutual induction. Have you got it now? If you want to ask any doubt here, then you can ask me. Means I have taken a small element dx
Yes, sir.
of this wire. First, I have calculated the induced EMF in this small element of the wire. And after that, for calculating the total induced EMF across the ends of the wire, I have integrated it. Okay. We have used integration many times now.
Yes, sir.
So we use integration to add small things. So here you are just calculating the induced EMF due to this small element, and when you will do the integration, there are infinitely small elements in this wire. So due to those elements, the induced EMF will be added up, and we will get the total EMF by using the integration. I hope that you have understood that.
Yes, sir.
Should I move now?
Yes, sir.
Should we discuss in the next class, or should I start the mutual induction? Are you able to bear it?
Hmm.
If you are able to bear it, then it's okay. Otherwise, if things are going out of your head, then there will be no use of that.
So I think you should start because I have tuition tomorrow after this one. So yeah, I think you should start it now.
I should start now?
Yes, sir.
Okay. Okay, so mutual induction is based on the same concept of the magnetic flux as we have discussed
Yes.
earlier. Magnetic flux, remember the term magnetic flux.
Okay, sir.
And remember the formula of the magnetic flux is given by BA cos theta.
Yes.
And what is theta? Angle between area vector
and magnetic field.
Yeah, angle between area vector and magnetic field vector.
Yes, sir.
What will happen when the magnetic flux will change? There will be induced EMF.
Induced EMF, yes.
d phi by dt.
Yes.
This is given by Faraday law.
Yeah. Yes.
Okay. Now see. We have two coils.
Yes.
We have two coils and coil number 1 and coil number 2.
Yes.
Coil means you have just wounded the wire in the helical form. That becomes the coil.
Okay, sir.
We have solenoid now.
Yes, sir.
Okay, so coil is same as that of solenoid.
Okay, sir.
Okay. So we have two coils here. One coil is this, another coil is this. And this coil is connected with the battery.
Yes.
And this coil number 2 is connected with the galvanometer.
Yes.
So there will be a magic here. Why magic? Because when I will close this circuit now,
it will be complete.
There will be the deflection here. I am just closing the circuit here, and there is a deflection here, and there is no physical connection between the coil number 1 and coil number 2.
Yes.
This is the beauty. Why this is happening? This is happening due to the mutual induction. This is happening due to the mutual induction, and that I am going to explain you the mutual induction. That is why I was asking, are you able to bear it or not? Okay. See now.
Okay, sir.
Initially, this is open.
Yes, sir.
So there is no current in this coil?
No, sir.
There is no current in this coil. Okay. Just think, I have closed this circuit. So there will be some current. There will be some current in this.
Yes, sir.
This current will also go in this coil. And I have told you the solenoid, whenever there is a current in the coil or the solenoid, there will be the magnetic field.
Yes, sir.
There will be the magnetic field. So what will happen? Due to this current in this coil will produce the magnetic field.
Yes, sir.
Just remember, this coil will produce the magnetic field, and that magnetic field will be at this coil also?
Yes, sir.
Are you able to imagine or not?
Yes, sir. Yeah.
Means this coil is producing the magnetic field.
Yes,
So
sir.
there will be some magnetic field here also.
Yes, sir.
Okay.
Okay, sir.
Like you can say that this coil is now will behave as a magnet.
Yes, sir.
This
Yes.
coil will behave as a, I have told you a current carrying coil behaves as a magnet.
Yes, sir.
So this coil will behave as a magnet. So you can imagine this as a magnet, this is as a coil,
Yes, sir.
this as a magnet, this as a coil. So due to this magnet, there will be some magnetic field at the coil too. Is it or not?
Yes, sir. Yes.
Okay. Okay. Relax. Now, when the current in this coil is increasing, suppose now I am just increasing the current in this coil, coil
Yes.
number 1. I am increasing the current in coil number 1.
Yes, sir.
See, I am increasing the current in, what will happen? Magnetic field
Will increase.
due to this coil will increase, due to this coil will increase.
Yes, sir.
So you can say here also the strength of magnetic field will increase
Yes, sir. Due to coil 1.
due to coil 1. This thing is clear. And
Yes.
I have told you the magnetic flux will be directly proportional to the magnetic field.
Yes. Yes, sir.
So magnetic flux linked with the coil 2 is directly proportional to the magnetic field produced in coil number 1. Is it or
Yes.
not?
Yes. Yes, sir.
Okay. So you can also say that if you will increase the current, this magnetic field will increase.
Yes.
If you will, you can say that magnetic field in coil 1 is directly proportional to the current in coil 1.
Yeah.
If you will
Yes.
increase the current in coil number 1, your magnetic field will increase.
Yes, sir.
The strength of the magnetic field.
Yeah.
So you can say that the magnetic flux in coil number 2 is directly proportional to the current in coil number 1, because
Yes,
when
sir.
you are increasing the current in coil 1, the magnetic flux is increasing in coil number 2.
Yes, sir.
Is it or not?
Yes, sir.
Yeah. This is the thing.
Okay, sir.
So phi 2, what is phi 2? Is the flux, magnetic flux linked with coil
Coil 2.
2.
Coil.
So on increasing the current, the magnetic flux is increasing here, and increase in magnetic field will produce the magnetic
flux.
not induced EMF.
Yes, sir.
Increasing in current will produce the induced EMF, and due to that induced EMF, there will be induced current. That is why there is a deflection in the galvanometer.
Yes, sir.
Now, have you understood why on on closing this switch or on increasing the current in this coil, there will be a deflection in this galvanometer?
Yes, sir.
Because there is an induced current in coil 2 due to the
Yes.
current in coil
Coil
1.
1.
So this is known as the mutual induction. And what is phi 2? Phi 2 is the magnetic flux.
Induced
No.
current.
Magnetic flux linked with coil number 2.
Yeah. Okay.
Linked with
Yes. Coil 2.
coil 2. I1, this is I1. I am representing I1 is the current in the coil number 1. What is V1? Magnetic field
Magnetic field.
due to coil number 1.
Yes, sir.
So I have already written the statement here. Whenever current in one coil change, EMF is in the neighboring coil. Due to the change in the current in the coil, flux linked with the coil will change and EMF is induced in coil number 2. Okay.
Okay, sir.
Okay. There is one more thing here. Now this is clear that magnetic flux in coil number 2 is directly proportional to the current in coil number 1.
Yes, sir.
So when you will remove this proportionality sign, you will get one constant, and that constant is given by and is known as coefficient of mutual induction. Okay,
Okay.
coefficient of mutual induction. And this coefficient of mutual induction depends upon several number of factors: separation between the coils, orientation, geometry of the coil, nature of the material of the coil. Okay.
Okay.
Okay. So now take the screenshot. Just I am zooming it. Should I zoom in? Zoom out.
Yes. Enough. Yes.
Okay. So you should know why there is a deflection in the galvanometer when you are increasing or decreasing current here.
Yes, sir. Done. Sir. Done, sir.
Tomorrow in half an hour or in 1 hour we will finish this chapter.
This EMI, sir?
This
Okay.
EMI, electromagnetic induction.
Okay.
Then we will start the alternating current.
All right. Okay.
Write down this one.
Done. Sir.
And Ziyad, please do one thing in the next class. When you are coming to the next class, when you will attend the next class, revise your notes of EMI only.
Okay, sir.
Hmm. So take the screenshot of this also. This
Done.
M is the coefficient of mutual induction.
Done, sir.
Okay. So Ziyad, just tell me what is now completed now. So I am stopping here. So now just tell me. I'm just asking, just discussing. Uh, what is the Faraday law for Faraday's law of electromagnetic induction? So Faraday law of electromagnetic induction says that whenever there is a change in the magnetic flux, what change in the magnetic flux linked with the coil, there will be the induced EMF.
Yes.
Okay.
Okay.
So what is Lenz's law?
Lens law.
Lenz, Lenz, Lenz. Okay. So according to the Lenz law says that the direction of the induced EMF is such that it
It
always
opposes.
opposes its cause. What is
Yeah.
the cause of the induced current? That is the change in the magnetic flux.
Yes.
So Ziyad, please revise your notes. Okay.
Okay, sir.
You should know the basic things at least. What is the Faraday law?
Okay, sir.
What is the Lenz law? If someone is asking, explain the mutual induction. So make sure that you are able to explain him. Okay.
Okay.
Why, if someone is asking that I am taking one coil connected with battery, another coil connected with galvanometer, if I am increasing current in this, why there is a deflection in the galvanometer? There is no physical connection between the coil 1 and coil 2. So you should know how to explain these phenomena.
Okay, sir.
Okay, Ziyad.
Okay, sir.
So we will meet in the next class, and please revise your notes.
Yes. Thank you, sir.
Okay, thank you. Hello, Divyangi.
Good evening, sir.
Good evening. How are you?
I'm fine.
Okay, so do you have any doubt regarding the last topics we have discussed?
No, sir.
Okay. Have you revised your notes? Hmm? Okay. So in the last class, I have discussed the horizontal projectile. Okay, from some height. Suppose